Hi, folks. Welcome to the Monday seminar. It's my pleasure to announce that Fabian Barras is going to give us a talk today. I hope you saw the announcement by email. It's the formal part of the announcement, I suppose. We like to keep this part of it informal. We would ask everyone to mute themselves at the beginning, but to feel free to unmute and just ask a quick point of clarification along the way. Yeah, if you have at the end, so let's save substantive questions to the end, because we'll have a nice long time for a question and discussion period led by Fabian. So yeah, please keep track and be prepared to join the discussion at the end. But in the meantime, I'm going to turn things over to Fabian. Thank you very much for putting this together. I'm looking forward to your talk.
Yeah, thank you very much, Chris, for the introduction and the kind invitation. And first of all, I also like to thank you and the rest of the organizer of this wonderful seminar series. And I have a background in computational mechanics, actually. I'm not directly from this field, and I have to say that I enjoy a lot and learn a lot also watching the previous talk at the Monday seminar. So yeah, thanks for setting this up. And thanks for inviting me to participate to this seminar series. And today I will present my work that's about how does frictional rupture propagate. And that's the work that involves many collaborators. I cannot fit all the names on the title page, so you will see the picture and the acknowledgement of this collaborator during the talk. And at the moment, I'm a researcher at the University of Oslo, precisely at the Njord Center, which is a center at the interface between the geoscience and the physics department at the University of Oslo. And I will just put a timer to keep track of how long I am presenting. So yeah, as I was saying, Oslo is a wonderful place to study friction, and that leads to this picture that we have seen during the setup. It's my feet stepping on icy sidewalks in Oslo, and yeah, during the winter season, it's quite frequent that we can do this type of frictional experiment when we are working in the city. And what is always surprising is how quickly the frictional strengths can suddenly disappear or drops and leads to a dramatic failure. So that's really an everyday experience of the nonlinear aspect and dramatic aspect of friction. But actually, if it feels that the friction drops suddenly when we are sliding on top of ice, I'm sure that if we will image that process or what's going on at the interface between my shoes, the sole and my shoes and the ice, it will most probably be a propagation of a dynamic or a rupture front that will breaks or drops this strength between the shoes of the sole of my shoes and the ice, and it will start at some place at some weak spot and probably invade the rest of the shoes and lead to the macroscopic sliding. So that's an assumption that I made, but this has been actually observed and imaged during decades of what is called Laber's-Quakes experiments. So it's a setup that has been widely studied in the lab. Here you have an example from Ilya Svetlitsky and a group of Jay Feinberg of such setup, where you have the two blocks that are pressed together in frictional contact, and you shear them until you get frictional sliding, basically stick-slip motion. And if you look at what's going on at short time scale during the onset of macroscopic sliding, you can see, and that's what Ilya imaged here, looking at the drop of the area of contact, how a rupture front nucleates here from the side of this box or this interface, and then propagate and progressively unlock the contact between these two blocks and leads to microscopic sliding. And they have been capable remarkably using strain gauge measurement also at the interface to show that this propagation of the rupture front is actually agrees quantitatively with the prediction of dynamic fracture theory. So that's a frictional rupture at the scale of the lab or of the shoes. But such rupture front are also observed or expected to arise at the scale of tectonic fault. Here I brought an example from the 2033 magnitude 7.8 earthquakes at the border between Turkey and Syria. And what you see here, it's a data-informed rupture simulation that reconstruct or reproduce the most likely rupture dynamics that arise during the setup. This computation have been made by this group here of the group of Alice Agnès Gabriel. And when I will play the movie, you will see the slip rate along this fault, that is the fault zone between the tectonic plate along the East Anatolian fault. And you will see that it nucleates at some point here. And then you have the propagation of this rupture that in this case unlock frictional sliding between the two tectonic faults and initiates the seismic slip and the earthquakes dynamics. So this is the type of ruptures that I want to study and discuss in this talk. And if I have to briefly highlight few scientific questions that I will mention. The first one is what drives the propagation of this frictional rupture at different scales, from the lab to larger scale, the scales of the fault. And the secondary question that I will also discuss is how can we use the dynamic fracture theory to build prediction? Can we predict, for instance, using dynamic fracture when this rupture will arrest, how it will arrest? Can we build some quantitative prediction on the propagation of this rupture? And I think this can be of interest, for instance, when we wonder what is the size of an earthquake, because if this earthquake would have stopped at this first junction, it would have probably been a completely different event. So first, I need to also introduce what I meant by dynamic fracture event. So I brought here this nice video from a YouTube channel, maybe my second favorite YouTube channel after the one of the Monday seminar. It's two YouTubers called Slow-Mo Guys that are basically, they have a high-speed camera and they image different physical processes, often failure or ruptures of material. And here what they did is that actually they break this slab of tempered glass. So if you look at this process with the naked eyes, basically they cut it here with a bolt cutter. It's really an explosive event, like you have a shutter of fragments. So it seems like really an explosive and dramatic event. But imaging this with a high-speed camera, you can actually see that everything initiated by the propagation of a dynamic rupture here from this nucleation point that is made by the Bowler cutter, and then that propagates quickly from the left to the right to the left and breaks the materials. And here also the speed, typically kilometer per second, that's also the same type of speed that is observed in frictional ruptures. So that's an interesting analogy. And that's what I meant by dynamic fracture. And interestingly, there is a well-established framework that has been developed to predict dynamic fracture in brittle material. And I will just briefly recall the few concepts that are needed for the rest of the talks. But I've seen that in past talks, there are already been a lot of great introduction of linear elastic fracture mechanics. So I try to be brief. So basically, if you look at zoom at one of these cracks, here you see the tip of a crack that move at some velocity. What's the driving force of this dynamic crack propagation? It's basically a drop of the stress-bearing capacity. So in the wake of the crack, the material is broken. It cannot withstand stress. So that's what you see here in the stress profile. You have this dark blue area because you have stress that has been released by breaking the interface. And basically, this stress that is lost in the wake of the crack has to be transmitted or is forwarded to the region of the material ahead of the crack, and it causes this stress concentration. And we can study this stress concentration, particularly the singularity that arises if we have a perfectly linear elastic material. And to do so, the basic idea or assumption is to impose a generic boundary condition that is expected to arise for perfectly brittle fracture, which is a stress-free condition along the crack surface. So that's what you see here along this crack. The theory assumes that you have zero stress, and that's perfectly fine for fractures because you have created a free surface, so you have no stress. And if you have this condition met, you will have the well-known square root singularity. So the stress follows this r to the square root minus 1/2 when you approach the crack tip. So that's an important assumption that we will discuss how this assumption can be met in the case of frictional ruptures, but it's an important assumption to keep in mind. And why is it important also this to know, to look at this singularity? It's because those singularity as what transport energy from the large scale down to the small scale. So in fracture or in a rupture problem, there is often energy that is stored at a macroscopic scale. Let's say the scale of the continuum, the elastic continuum, kilometer scale, for instance, in the case of earthquakes. And then this energy during the rupture has to be is flowing and has to be transported down to the tip of the rupture where all the rupturing process and the damaging process arise. And this is done by the stress singularity, or it is governed by the stress singularity. And if you have the square root singularity, the theory predicts that knowing this singular contribution, you can estimate, or you can actually measure what is the flow of energy flowing from the macroscopic scale down to the micro scale at the rupture tip. And that's something that can be done. So I will spend a bit of time to discuss this plot because it will come back at several times during the presentation. So basically here you have the distance along the fault along the x-axis, and you can see at the rupture tip, if I zoom, both the shear stress. Here it's exactly the same than what you see here. When you approach the crack tip, you have the stress that increase, reach a peak value, and then drops to 0 in the wake of the crack. The slip velocity is doing actually the opposite. So it's initially 0, but then when the material is broken, it quickly reaches a peak value, and then it decays following the square root singularity as well. And using the near tip singular prediction, you can actually fit at the same time the slip rate and the shear stress. And from this, if you know, for instance, the speed at which the crack propagates, this will give you this alpha S. You have tau C that is just the peak stress that you can measure as well. So the only parameter that you're left with is this GC, so a fracture energy or measure of the energy that is flowing to the crack tip. And if you are modeling, like in this case, classical fracture mechanics problem, that's typically an input parameter of your system. So I can verify fitting or plugging this, fitting this solution that what I measure here as an energy transported to the crack tip correspond to what I input as a material properties of my system. So that's for fracture mechanics. And last comment that is also important to keep in mind is that in nature and in this simulation, for instance, we can see that the stress and the velocity, they are not exactly singular. At some point, they are regularized and reach a peak value inside of this blue box that is called the process zone. So that's because the material is linear elastic only outside of this region. And in this region, you have non-elastic, non-linear processes where material is being damaged. And what the theory predict and why it has been also so successful and so successfully applied to predict dynamic fracture and the crack propagation is because as long as this process region is small enough compared to other length scale of your problem, you can use the theory and predicted by dynamic fracture, and you can use a GC as a parameter or the stress singularity as a way to compute the flow of energy to the crack tip. And once you know this flow of energy, you can predict if the crack will grow, if with this energy balance, how fast it will grow, if it will stop, etc. So yeah, if you have any question, just don't hesitate to interrupt me, but otherwise I will continue. So now, as I said, when we are dealing with frictional rupture, it's a bit less clear how this assumption can apply. And the first one that I've highlighted or underlined before is this zero stress condition in the wake of the crack. So usually the way to go and to fit frictional rupture in this setup is this slip weakening frictional model that is known for a while. And the idea is that in the slip weakening friction, that is, for instance, depicted here, you have your shear stress that reach a peak value, let's say a static friction coefficient. Then you damage your frictional interface, you reach a residual value, which could be understood as a kinetic friction coefficient. And then if this value stays constant during the rest of the propagation, You can use the linear superposition. That's all the interest of assuming a linear elastic material. So you can decompose this problem into a problem where you have just an interface that slides at this residual frictional value, and a fracture mechanics problem where you have, again, this well-defined fracture energy. And using this, you can see actually that a rupture inside or simulated or studied with a slip weakening friction, it's exactly equivalent to a shear crack in a shear fracture problem. And from this analogy, you can estimate what I will call here the breakdown energy, which is the energy that is dissipated on top of this residual friction value, which is the fracture energy, the analog to the fracture energy in the case of a slip weakening friction. So this is the energy that will control the ruptures. But the big question now is how this friction simplified or idealistic frictional rheology can hold for realistic frictional rheology and natural system, because it's highly unlikely that there will be a well-defined residual friction. That will be a bit the menu for tonight. And the approach that I will follow and that I had followed to study this is to run numerical simulation, where I typically couple macroscopic bulk linear elastodynamics that drives the propagation of the rupture, where I have stored elastic energy. And at the interface, I will use a frictional constitutive law. And instead of using, if I would use slip weakening friction, basically I can verify that I extract the fracture energy that I predicted. But what I will do and show you tonight is what happens if instead of this, I use a friction rheology that don't prescribe GC. Can we learn something from this? What type of frictional rupture first will emerge? And can we predict some coarse grain fracture mechanics quantity from it, like GC, delta C, etc. And I just, before starting, just like to show this nice figure from this review in 2023 annual reviews, where there was a nice job to compile different measurements that can be done for the energy budget of earthquakes at different scales. So you can measure the energy budget of earthquakes or of the seismic ruptures from the field, so directly looking at damage along exhume fault zone in the labs by seismologic inversion. And if you do so, you see that there is a broad variation of the type of rupture energy that you can estimate. And so that's something that is very fascinating to me. And I will also use this slide as a disclaimer, because I don't have full expertise and understanding on all the measurements and the detail of how these data are measured. So that's something that I will be very happy to discuss further with you afterwards, to see how we can map what we observe in simulation to these measurements in seismology or in the labs. So I will also use this plot to say that in this presentation, I will only talk about rupture energies. That's why I replace fracture energy by rupture energy. So the idea is that it's only the energy that will control the propagation of the rupture tip. It don't have necessarily have to do with fracturing process. Here I will just look at the energy, the flow of elastic energy to the rupture tip that drives the propagation of my rupture in simulation. And so that's what I will call rupture energy here. And it will be interesting to discuss afterward how we can use that to describe, for instance, the earthquake energy budget. Okay, so that's a bit the outline of the talk in the form of a spoiler. So what I will show tonight is that the emergence of crack-like dynamics. What I mean by this is that a dynamics that is in quantitative agreements with dynamic fracture theory arise for broad type of frictional models. So that's something that was quite interesting, is that if I will show you two examples tonight, basically one with rate and state friction and one with the shearing of a gouge that has some thickness with thermal pressurization. So two systems that are quite different, but in both systems, we see the emergence of this rupture dynamics that agrees well with dynamic fracture theory. Also, what is interesting is that this is not systematic. We will see also a case of rupture that propagate, but that do not follow or diverge from the prediction of dynamic fracture theory. And what is interesting from this model is that from the interplay between the micromechanical frictional rheology and the large-scale elastodynamics, it is possible to pinpoint the physical origin of some coarse-grained quantities, such as the fracture energy, that will be useful to make prediction of the propagation of this rupture. Something that is quite interesting in this discussion also of what is the budget of this frictional rupture is that the rupture energy, meaning the energy that drives the propagation of the rupture, does not necessarily relate to fracturing process. For instance, we will see in a case where the process behind rupture energy is strain localization. So the interface completely lose its strength because the region that bear the shear stress is suddenly reduced. And that's what caused the failure of the propagation of this rupture. So it can be completely decorrelated to any fracturing process per se. And also it can be significantly smaller than the measured breakdown energy. So I show here a cartoon of what is typically observed in simulation is we have often a very sharp rupture breakdown or reduction of the frictional strength, followed often in this realistic model by some relaxation, some long-term evolution of or weakening of and reduction of the shear stress. And usually what drives the rupture is this initial small rupture energy. And I will show in conclusion also that this energy partitioning that I draw here can also significantly change throughout the rupture, and it's not necessarily universal. And that's interesting. And also when I mean throughout the rupture, it also means that it can evolve between different or earthquakes with different magnitudes. That will be a bit the last part of the talk. Okay. So let's start with the first type of model. So that's a bit where this whole story started when I studied frictional rupture was with using rate and state friction. And that was back at the time of my PhD studies under the supervision of Jean-François Molinari. And this was a collaboration that we had with Thibaut, Efim, Michael, and Eran. And in this first type of model, the frictional rheology that was used at the interface is rate and state friction. So we tried different version of the rate and state friction. So this laboratory derived friction law. And what is interesting is that in rate and state friction, you don't have a residual stress that is an intrinsic residual stress inside the friction law. It's something that emerged from the interplay between the solid elastodynamics and the rate and state friction at the interface. But even in the absence of this well-defined residual stress, we see the emergence of crack-like dynamics. And here I will show you again, this is the same type of plot that I've shown you before for a classical fracture simulation. And it's hard to see any difference because it's really similar to a very quantitatively similar to a propagation of classical shear cracks. I will just highlight one difference here is that if you look at the shear stress, it's not completely going directly towards zero as expected in the wake of a slip weakening model or shear fractures, but it takes some long time or long distance in this case because here it's space for friction to weaken, to keep weakening far from the rupture tip. So that's one difference that we observe. But we can then also extract as in the case of dynamic fracture, measure the flow of strain energy to the rupture tip and compute the rupture energy GC associated to this. So I won't give too much detail about this also because this work, because it has been summarized in a previous TECTONIC fear seminar by Jean-François and Thibaut. I think it was in 2023. So if you want to have the detail about what type of friction law we used or how Torres is selected or in this process, you can refer to their talk or also to the paper that discussed this. What I want to show here is that what we observe is that this fracture energy is also smaller than the breakdown energy. And these two differences that we observe, a smaller fracture energy than the breakdown energy, and some non-constant residual stress, that indicates some deviation from what the theory for linear elastic fracture mechanics imposed as an assumption. And there was an important follow-up work that has been done by Efim and Eran that is summarized in this paper to show that even indeed there is a slight difference or slight divergence between the frictional rupture that we simulated with rate and state friction and dynamic fracture theory. But if this difference is subtle, you can still well approximate the dynamics of the rupture by mapping it directly to a dynamic fracture process. And that's what you can see here, for instance, this small deviation when you look at the breakdown work. So that's the curve that can be integrated from the numerical simulation. So if it will be a slip weakening process or perfectly brittle dynamic fracture cases, you will see that when you reach GC, you will have a plateau. So you will saturate at this value. You won't have further weakening. Here we can still map a small increase after the GC that is measured or inverted from or measured at the tip of the rupture. You can still see that the breakdown work keeps increasing, but at a very slow pace. So you have this apparent plateau. And that's also a way to measure from this. You can predict that if this plateau is really flat, it highlights a slight deviation from singular prediction or square root singularity. But dynamic fracture theory, it's still a very good approximation, and GC, very good metrics to measure and to describe the propagation of these ruptures. And this is important because I will use also this aspect later in the talk. So let's move to the main part of this presentation. It's the study that I've done with Nicolas Brantu at the time, mainly at the time where I was visiting him at UCL. And so that's the study that Nicolas was asking me about the status. It should soon be resubmitted in NatureCom. It's currently under review. And the idea here is what the main question is, what about now fault friction? So far we have only considered perfect interface or interface that are nominally flat. But if I look here at a sketch that have been produced in this review paper, how the fault or friction in a fault should emerge in mature fault zone particularly. It emerged from a sheared volume of fine-grained granular material. Here, this PSZ, principal slip zone, that is typically a few millimeters of size and that accumulate most of fault slip. So in this case, it's really a volume of material that is sheared that will produce the friction that is felt by the rocks at a macroscopic scale. And this volume of material, it introduced another dimension or transverse problem that is here. I highlight with the variable y. I will use x for the along the fault and y for across the fault. And you can look through the gouge that is sheared. You will see typically this profile of slip rate. So the slip rate change at different position along the gouge. And if you take the derivative, that is what is interesting here, or the slope of this profile of slip rate, you will obtain the strain rate, which is a function of which change across the layer of gouge, but also can evolve through time. And that's a bit the question of the setup of the problem that we want to study, and particularly the possibility for this profile of strain rate to evolve also and to concentrate on smaller region and to localize basically. So here I can identify a region that is actively slipping from this profile and a region where there is almost no strain rate. And this is what will define a length that is called localization length. So to study this process, we build and follow up on a 1D model that has been proposed by Rice, Platt, and Rudnicki in 2024 mainly. And this is a model where they solve in 1D, so in this y direction, a thermal pressurization problem. So they have a frictional rheology that looks like this. It has an effective stress or normal stress contribution. You have an initial or normal stress that can be reduced by some pore pressure inside the gouge, because these gouges are typically assumed to be saturated with fluid. And it has also a friction coefficient that has a slightly rate hardening rheology that depends then on the strain rate gamma dot. And that's the rheology that is assumed in this model. And how pressure is evolving is via this coupled diffusion equation that relates pressure and temperature. So that's a well-established model for to model thermal pressurization in the context of earthquakes. So as you shear, you produce some heat, and this heat is increasing the pore pressure inside the gouge just by the difference in the thermal expansivity of the pore fluid and the solid matrix. And you have this thermal pressurization term that couples this. Is there a question? Okay. I was scared that I say a mistake and someone was mad at me.
I don't think she was asking a question. I'm not sure.
Okay. Well, anyway, so in this model, you have three spatio-temporal variables: pressure, temperature, and most importantly here for us tonight, this strain rate that can evolve both spatially and temporally. And you have some boundary condition, can be either controlled under some shear stress that can change with time depending on the evolution of pressure, temperature, and strain rate, or it can be also controlled in slip rate, so you can impose a differential slip rate between the top and the bottom of the gouge that is just the integral of the strain rate over the thickness h. So that's a 1D model that was capable of reproducing some localization features in one dimension. But what we were interested is to couple this to the propagation of this localization, how this propagates over kilometers. So that's challenging because here we have a small scale millimeter problem at the micro scale. And we have really a scale separation or multi-scale problem because the propagation, it will arise over kilometers. So this is a challenge, but also a chance because we can really decouple these two problems, and that's what we did. So we assume an elastodynamic boundary integral method where here we discretize only the fault between or the contact plane between the two sides of the fault. That's this blue dot here. And at each of these points, we will solve independently the 1D model of thermal pressurization of Platt, Rice, and Rudnicki. And that's how the model is built. And if we look at the equation governing this model that is here, it derives from the classical equation for elastodynamic boundary integral method. So you have shear stress along the fault. It's given by an initial stress, like the stress that has been built up. Some local response of the gouge here, so that's the term that locally relates the change in strain rate with a change in stress. And you also have, importantly, elastodynamic interaction that redistributes stress from one region along the fault to another. So if one region localizes, it loses its ability to bear stress, and then it forwards this ahead on the next region. So we have this fracture or rupture processes that will arise. And that's what you will see in this video. I hope we can play it. Where is my mouse? So this is just the different variables of the simulation that you can see. So you have here the macroscopic variables. As before, the red is the shear stress, the yellow is the slip rate, and here it's what's going on inside the gouge. So inside the gouge, we solve for pressure, for temperature, and for strain. And here we are mainly interested in the rupture dynamics, so we won't really discuss too much about nucleation. So we are doing a bit like the slow-mo guy in the dynamic fracture experiment with the bolt cutter. So our bolt cutter is just here, we increase pore pressure at the center just to trigger the rupture, and we monitor what happened far from this region. So here, let's see, the rupture will quickly start and spread laterally. So that's how the rupture event looks like. And here what is nice, you can see how the rupture tip is associated to change in pressure inside the gouge, elevation in temperature, and most importantly, it's all the strain that is accumulated in the layer of gouge is really inhomogeneous. So you really have a small region that really accumulate all of the slip and not the entire thickness of the gouge. So that's really the evidence of strain localization mechanism. And that is, in this case, the driving mechanism of this rupture here. And that's what I will show you quantitatively in the following slides. So first, let's zoom near the propagating tip and see what's going on. So here you have the stress concentration, you have the velocity that quickly rise. And if we look what's inside the process region, we can directly see or easily see that it's intense strain localization that is arising. So let's look at 4 points. If I am ahead of the crack, so here the rupture propagates from right to left. If I'm ahead of the crack, point A, basically I have low strain rate and homogeneous strain rate across the gouge. When I approach the rupture tip, point B, I start to accelerate the strain rate and I start to see slightly larger strain rate at the center of the gouge compared to the boundary of the gouge. And when I reach the peak velocity, I have really an intense strain localization. So here the strain rate at the center of the gouge is several orders of magnitude larger than what happened at the edge of the gouge. So really the peak slip rate is really coincide with the most intense localization of strain. And what is interesting is that we have a sequence of localization, but then delocalization. So if I look in the wake of the crack, point D, the strain rate profile has again delocalized a bit, and it's progressively strain is delocalizing. So we have this sequence of localization and delocalization at the tip of the ruptures. And we can, if we again do the same type of study where we plot on the same plot the concentration of shear stress, the concentration of slip rate at the tip of the rupture. Here I highlight again this blue region that is the process zone. We can fit nicely linear elastic or dynamic fracture theory, and we can highlight a process region that is in this case intimately related to localization process inside of the food. And we can go a bit further to test. So this will allow us, again, to extract or measure at different time and different position along the fault what is the flux of strain energy from the elastic material toward the crack tip. And we can compare this macroscopic measurement of energy flux to what is dissipated in the micromechanical model. So that's what I will do now. I will look inside the gouge at different position along the fault, what's happened when the earthquakes is passing by. And here it's so this is just a visualization that I made to visualize what is happening in terms of strain localization. So I just displace an artificial granular packing. So it's again what we simulate is only 1D problem. Here I just put some dimensions so you can easily visualize the strain and its evolution throughout the ruptures. And here I plot dynamically, you will see the strength of the gouge at this location and the accumulated slip. So initially, you will see that that's more or less what, oh, no. Not so easy to pause this video without, if I go here. Yeah, the initial part is really similar to what would be called in case of fluid, simple shear flow. So we just have an homogeneous strain rate, and more or less the strength is it's constant in this phase. Then you will see that as the rupture approaches, the stress will build up, and then we'll have a rapid localization and the acceleration of the slip. And that's what we can measure at different points of the gouge, and we can look at how stress evolve throughout the rupture. So I will play it again so you can see how this material rapidly localize. And this rapid localization, it's again what caused dynamic rupture propagation. So I can look at different position along the fold. The nucleation here is at x equals 0. So then I have different points or different position along the gouge. And what I see basically, if I start from this plot, is that I have the slip rate that rapidly increase, reach a peak, and then following this peak decay. And if I look at the profile W log, so how localized is the strain rate at each of these steps, it's what I've shown you already before when I look at the snapshot. Initially, I have a localization sequence, and when I reach peak stress, this is followed by a delocalization. And I can really identify that before the peak, it's a localization process. After the peak, it's a delocalization process. What is also striking is that different regions along the fault, they reach peak velocity for the same amount of slip. So it's something that is really close to a critical slip weakening distance, because the peak velocity at different part of the gauge is always observed for the same cumulated amount of slip. And if I look at the evolution of stress, that's what I show. It's a bit the same type of profile that we have shown before in the video of localization. Initially, I start here. The stress builds up when you approach the crack, and then you have this rapid and catastrophic loss of stress-bearing capacity when you have intense localization. And then you have a prolongated or an extended weakening that keeps going on, because you still slide at some velocity and you have further pressurization and heating of the gouge material. And here, what I highlight in this gray area, it's what corresponds to the dissipation that is measured macroscopically as an energy flux from the large scale down to the rupture tip. So we can see that this corresponds quite well to the phase of the weakening phase that is associated to strain localization. And we can go a bit further and look again at the breakdown work. So if you remember the case with rate and state, I mentioned the importance of this plateau to observe the development of small deviation from linear elastic fracture mechanics, but very small, and we can still use the theory quite well. So that's also what we observe in this case for thermal pressurization with strain localization. We have this clear plateau where we have rapid dissipation of energy, then a plateau. And what is a bit new or different than the case with rate and state is that here we can see a second weakening mechanism that kick up for large amount of slip. But we still have decades of slip between this first mechanism and the onset of the second one. So these are two mechanisms that are split or temporally and spatially along the fault. So we can call that a near-tip weakening mechanism that will be strain localization, and a tail weakening mechanism, in this case, that will be further pressurization and heating of the gouge. And what is interesting, we can again test independently with what has been measured from the profile of stress, the energy flux to the crack tip, and it's almost constant at each of these points. And I just put here a gray line that correspond to the value that we measure, and you can see that it coincides really well with the plateau, and as a further confirmation that this is really this first weakening mechanism and rapid strain localization that controls the propagation of the rupture tip. And we have again this picture that I've shown in the spoiler, a rapid drop of stress, quite very brittle, that drives the propagation of the rupture, followed by a further breakdown energy and further weakening. What is interesting is that during this paper, we are also wondering what happens if now we remove the possibility for strain to localize. Because that's something we can do with the model. We can just impose a fixed profile and say that the gouge is allowed to pressurize and heat, but it's not, the strain profile is not allowed to change. And that's what we did. And if you do so, you completely kill this plateau. So you have this other dynamics that is shown here by the brown curves. And what is nice is that in this case, you still have a rupture front, but this rupture significantly diverges from linear elastic fracture mechanics prediction, because you are not able to identify a near-tip weakening mechanism from a tail weakening mechanism. So here what result is that we have singularity that significantly diverge from the square root singularity. And we have also a rupture that is governed by a much larger energy dissipation compared to the blue one. And I have to say, I forgot to mention that between blue and brown, it's exactly the same identical properties for the gouge, for the fault. The only difference is the possibility to localize or not. And why, or a way to see that, for instance, what is the consequence of larger energy dissipation is that we need almost twice a larger nucleus to trigger the rupture when we prevent the interface to localize. So it has direct consequences. And this is due because now the wall, not only the near tip dissipation is accounted, but all the frictional dissipation along the entire slipping patch plays into resisting the propagation of the rupture. So that's an interesting case also to highlight when dynamic fracture is not working. But what is interesting is that strain localization is a mechanism that causes the embrittlement of fault friction because of these features. And in this case, in the blue case, the blue case could have also have the possibility not to localize. So it's interesting that when we have the possibility to localize, that's the mechanism that is self-selected by the coupling between the fault friction and the elastodynamics. Okay.
Fabian, sorry.
Yeah.
Just a quick question.
Yeah.
The previous figure, when you say that you reach the rupture energy at the plateau, I see the x-axis that you are at 10% of the ratio between sleep and DC.
Yeah, so that's because I don't use the, so it's also the same or less, yeah, here. So it's not really I should maybe put DC corresponding to this one if you really want to have the DC of an equivalent sleep weakening process. But here we use the D sub C of thermal pressurization.
Okay. Now I understand.
So but that's a really good question, I think.
Okay, now it's clear because I didn't understand why is only 10% to reach the total rupture energy.
So the DC of a sleep weakening process will be almost like the one here, maybe a bit shifted. It was 0.3, so yeah, around here, yeah.
Okay. Thanks.
So the different shades of blue, Fabian, are different velocities. So the faster the crack goes, the tighter the near tip region becomes.
Sorry, the faster the
faster the crack, then you get a shortening of the process zone. Is that true?
Exactly, yeah. Okay. And we also I don't have I think I don't put this plot in the presentation, but we can see it here. We also have a shortening of the process region, but also of the if I put the last also of the localization region. So initially when the crack is low, close to the nucleation, it's localization, the max localization that you get, it's quite broad. And then it's really drops with the propagation speed. And we can have a prediction. I think I did not put it in, can check later if I have the slide in the extra slide. But we can have a one-to-one relationship between the thickness of the localization thickness that is observed in the gouge and the velocity of the rupture tip at some position along the interface.
If you turn off pore pressure, you still get the strain localization due to the thermal part, correct?
Yes, yeah, that's exactly true. So, but I will need, it will be the case if I include some thermal softening mechanism. So here, the only way to weaken my stress is via the pressure. The temperature is not directly entering into this equation, but I can imagine a material law, for instance, thermal softening for metals, where you will have a drop of the shear strength with temperature, and it will have exactly the same effect. So that's something also that we discuss in the paper, is that we have picked here thermal pressurization as an example where we have strain localization, but we suspect that many other processes that involve diffusion of temperature, for instance, and weakening can produce the same physics and the same rupture dynamics here.
Thanks.
Okay, so I think I was at the conclusion of this first part. So we have seen the emergence of crack-like dynamics. I think I was quite at least surprised and found interesting that with this different type of frictional model, we observe really the same type of rupture dynamics for the propagation of this rupture front and their agreement with dynamic fracture. So there is always a slight deviation from linear elastic fracture mechanics, but sufficiently small to still be able to extract a well-defined fracture energy and use fracture mechanics to describe them. I also see that it's not systematic, but when the system is freely able to evolve, like in the case of localization, if we allow localization, the system will tend to produce this dynamic fracture or brittle ruptures. And I think the physical explanation behind it is because it's an inefficient way to break the fold. It causes an embrittlement of the fold by this very sharp drop of the stress-bearing capacity. And we have seen that in this case, a generic picture that works both for rate and state and also thermal pressurization is the following. So we have a rapid, we can call it brittle tip weakening mechanism that where the associated dissipation controls the propagation of the rupture, and a following tail weakening mechanism that make the rest of the breakdown energy. But now in the last minutes, I try to show that this is something that can also evolve as the rupture propagate. And that's a work that we have done together with the group of Marie Violet in EPFL. So it was the work together with Federica, François, Mathias, Marie, and also Nicolas. So they were actually able to measure, that was the experiment that Federica conducted in EPFL. They were able, doing this experiment of stick slip, to extract and to measure what is the rupture energy and the remaining breakdown work. So it's the same type of plot that I just show you for simulation, but this one is constructed from experiment between PMMA, and they observe the same type of physics, that the rupture energy is associated to this very rapid weakening in the beginning. That's what controls the propagation of the frictional ruptures. And you have some significant amount of breakdown works that can arise afterward. And if you want the details of this nice experiment, you can have a look again at the former Monday seminar that was done by François and Federica, I think in 2001, where they present, among other experiments, this setup. And at that time, we have several discussions between their group and Nicolas and myself about if this tail weakening can have any influence on the rupture, because it seems from the simulation and their experiment that only the near tip part was important, but what about this tail? So to answer the question, we did some simulation that were so detailed also in this paper. And the idea was to pick, in this case, an idealized slip weakening model, but not with one weakening stage, but with two weakening stages, when we can compare a first very brittle tip weakening mechanism with its associated fracture energy GC, and a second tail weakening mechanism that arises of a much longer slip weakening distance, but that can also have a substantial drop of the strength. And we conduct numerical simulation, and here you have the example for exactly the same properties, the same stress, the same nucleation properties. The only difference is in light gray, it's a simulation where only the first weakening stage is present. And in black, it's a case where we have the two weakening stage. And what is striking here is, if you look, so in this case, it's distance along the fold and slip rate. And you can track here the peak slip rate and its evolution along the fold. So it's also the rupture tip is again always correspond to the tip of the slip rate here that I'm pointing with my mouse. And what is striking is that these two simulations have exactly the same tip dynamics in this case, because the motion or the equation of motion of this tip, and that we can verify quantitatively by looking at the flow of energy to the crack tip, it is only controlled by the energy GC tip. GC tail has no effect on this. But it's still important to mention that it has a significant effect in what happened behind the crack. So here you see that at some point you have the effect of the second weakening stage that kick off, and the two curves depart from each other. And then if you look at the total slip that will be accumulated in the wake of the black curve, it will be much larger than what can be accumulated in the wake of the gray curve. So there is an effect in terms of the amount of slip, but in terms of the rupture dynamics, only the first GC tip matters. And that's a bit confirms what we are observing in the lab and in the thermal pressurization simulation. But then we were wondering, is there a case where we can force a bit or have the second weakening mechanism taking the lead of the rupture as well? And an interesting example for this is to put a stress barrier. So initially that was a bit like before, we have 90% of the peak stress. But now if you reduce it to 65%, obviously the first weakening mechanism alone will never be able to cross that barrier because it has only a stress drop up to 0.8, I think. So if you run the light gray curve before, it will propagate until there, and then it will be arrested abruptly. And what is interesting is that in the dual case situation, you can see that then the second weakening stage can kicks in and start to drive the rupture. And that's what you see here. You have this tip that now is growing. And you can see now that the first weakening stage is a small blip ahead of the main peak velocity that is governed by the second weakening mechanism. And we can again verify quantitatively this by measuring the flow of energy with the standard techniques, looking at how much elastic energy is flowing to the crack tip. So initially, it's a small value that corresponds to this GC tip. But when you reach the barrier, so here there is a small transient region because the dynamics become quite messy. But then you quickly converge to this value of the GC tail. So this part of the rupture is entirely governed by the tail rupture dissipation and no longer by the tip. So that was really an interesting observation as well, that the fracture energy or this additional weakening mechanism can also play a role. And I think an interesting thing that we can discuss is its application to what can arise in the context of earthquakes. So what is this interest of this two scale? Is that the first sharp, brittle initial weakening mechanism, it allows or it enables nucleation of a very small patch, because this is a very brittle. You don't need a big region or nucleation size to initiate rupture. So it has extremely small nucleation lengths. For instance, in this case, we won't be able to nucleate a rupture only with GC tail. You need this first stage to initiate the rupture in a very short region. But then the second weakening stage allows for earthquakes or seismic rupture to move forward and to also rupture portion of the fault that are under much lower amount of stress. And that's quite interesting because it fits well with this different energy budget that can be observed at different scale or different earthquakes magnitude, where small earthquakes tend to have smaller rupture energy. And it also fits well with a bit the puzzling observation that fault zone tends to operate at level of stress that are much lower than their expected strengths. And in this mechanism, it means that you only need a small region where you have either higher stress or higher pore pressure to nucleate the rupture with this tip, very brittle mechanism. And then if the rupture that has been nucleated by a rapid mechanism has the option to trigger a second weakening mechanism of a more substantial magnitude, it can enters or propagate into regions that are really lowly stressed. So that's a bit an interesting observation that has been made in this case. And I think I'm approaching the end of my talk and the end of my time. So I will just quickly mention that a third part also where if we go a bit further from in the earthquake propagation, that is interesting is the change of rupture dynamics that arise for large earthquakes. So this arises when the available energy dries up. So far I have assumed that I have an infinite bulk that can provide me strain energy. So the only limiting factor is the capacity to transport this energy from the large scale to the small scale, basically the stress concentration. But in this system, you are much more limited by the available strain energy. So the system starts to feel the boundary, feel the finite size. So here, for instance, it means we have a small edge that we can identify both in this strike slip setup or convergent setup. And in this case, at some point, you dissipate the energy that is accumulated there, and then you have no more energy, and that tends to promote a transition toward a slip pulse. So you slide for a while, and then the rupture or the sliding motion stops. And that's what can be seen, for instance, in this seismic inversion from the Ridgecrest event by Chen et al. So initially, what you see here is a map of the seismogenic zone, so basically this rectangle here. the rupture starts at this blue triangle. Initially, it grows like a crack radially. So that's all what this presentation have been about so far. But at some point, when it becomes big, it starts to feel the effect of finite size boundary, and you start to transition more from a crack-like rupture to something that is more a pulse that will propagate. And that's an interesting transition also that should be noticed when you, and it's also observed in seismic inversion, but also in 3D simulation of faults. And I just mentioned that, yeah, with François Renard and Einat from the University of Oslo and the Hebrew University of Jerusalem, and Shetil is also a colleague at the University of Oslo, we have developed a model where we can describe a minimal model to describe or predict the propagation of rupture front in this large earthquake setup. So why it's a minimal model? Because we can reduce a lot the complexity by the fact that the rupture becomes planar. We have a small scale, so h is much smaller than the rupture length. So we use all these approximation to build a 1D elastodynamics model that can be used to predict how far the rupture will propagate. And yeah, I don't have time to go too much into the detail, but with this 1D model, for instance, the type of simulation that we can do, we can also then study how this rupture, for instance, propagate, what is their energy budget that is different from the one that is governed by the stress intensity factor that I've shown in this presentation. And you can also predict, for instance, how fault bands in this case that you can map into variation of pre-stress in this simple model can arrest a traveling slip pulse. And I think the interest of this model is also that with the simplicity of the formulation, we have really cheap computation. So that's a 1D equation, and maybe it could be solved it has potential perhaps to be used in earthquake early warning system when you wonder when large earthquakes can stop and you have a limited amount of time to compute the rupture dynamics. So that was a bit a conclusive part or last part of the talk, that you have a transition of the energy budget from very close to nucleation to extremely large earthquakes. And I think I've been it's almost 1 hour, so I will stop here. I think the conclusion I have repeated it several times during the talk, so maybe it's time to thanks for your attention and start the discussion.
Thank you very much, Fabian. Really fabulous talk. I'll invite people to unmute. Otherwise, join me in thanking you for a great talk. Yeah, lots of interesting things.
Thank you.
Go ahead. Someone use. I'll just invite people to go ahead. Use the raise hand feature at the bottom of the screen. It's the easiest way to organize ourselves into I don't know, let's say a list of people who would like to ask a question or bring up a discussion point. We can give Fabian a second to catch his breath. But yeah, please raise your hand, join the discussion, everyone, because yeah, this is a nice opportunity to get some feedback to Fabian and also to have a discussion. Massimo, go ahead.
Thank you, Chris. So thank you, Fabian, for your very stimulating and excellent talk. Great.
Thank you.
So I have one comment and two questions. The comment concern, I think that we need to have a clarification of terminology, because the way between the breakdown work, breakdown energy, and fracture energy. Otherwise, we are referring. So by definition, the breakdown work is the integral below the entire slip weakening curve. So according to your and Federica approach, the breakdown work should include both the fracture energy and the breakdown energy, because it is the integral until some minimum slip distance or minimum stress level. And we don't know, so the way in which it was defined is completely independent of the energy dissipation. So it's just the work. Inside that area, you can have either. So it is nothing against what you presented, but the breakdown energy is the misleading term, because breakdown energy is defined as a difference, but it includes. So my comment is essentially we need to pay attention to terminology in order to exchange our ideas and that. So
Yeah.
my questions are, the first, in your simulation, in particular, the one when you have the dual weakening rate, what controls the switch between the first and the second?
So just first to clarify, I was not sure.
That figures, what controls the switch between rupture energy and breakdown energy?
So yeah, just to clarify, I think the breakdown energy in these figures, it's also include part of this it include everything.
Okay.
And it's maybe I should put some blue hash to, but yeah, it includes also the rupture energy.
We don't need that. The terminology is fine.
And in this case, what marks the transition is really this plateau that we've seen in the breakdown work plot. I can show that again. And this plateau corresponds to this sharp change in the weakening slope. So you have a brittle mechanism where this weakening slope is extremely steep, and then a second slope that is extremely flat. And this change of slope marks the transition. And if you plot this change of slopes in a breakdown work profile like this one, oops, I think I have this in the middle of the. If you plot the breakdown work, in this case, it will, with a sharp difference in terms of slope, you will have this horizontal plateau. And for instance, in the dual scale weakening, it will correspond to two curves that have this delta square slopes, but that are shifts, and some plateau that connects the two. And this change of slope marks the transition between the fast and the tail.
Okay. And the second question concerns the scale separation, because the way in which I interpreted the scale separation is that in order to have a modest breakdown of the scale separation, you need that outside the process zone, the shear stress is very close to the residual. But if you have this behavior, you might have a stress that is much different from the residual, which would imply a relevant breakdown of scale separation. Therefore, you should not be much consistent with linear elastic fracture mechanics.
Yeah, so that's precisely the difference between these two cases. So if you have no plateau, then it means that in this case, you don't have, you never reach almost constant residual stress after the first weakening mechanism. You have something that is progressive, and therefore you have a significant deviation from dynamic fracture prediction. And this here can be, as you said, it's directly related to the small scale yielding condition. It means that along your interface, you have an inelastic process or that stretch over the entire rupture patch. But when you have this sharp plateau, the stress, if you zoom at the crack tip, it's almost constant for a while before start weakening again. I don't know if I have. So here it's the case for instance, for the thermal pressurization. You see that it's really stay constant for a while before starting weakening again. If I put the case of Rayton state, yes, it's the same. So it's almost constant for decades. So there is still a clear length scale separation between the rupture process near the tip and some weakening that arise over much longer distance. And from the point of view of the tip, this is almost like a constant residual stress. So that's what allows to have this small scale yielding assumption that is met. And it still deviates from dynamic fracture. That's the work of Eran and Efim. You will still see deviation in this case, but if the deviation is minute, you can have a fairly good prediction of the dynamics using fracture mechanics.
Okay, thanks. But therefore, in this case, this means that actually the breakdown energy or the difference between the breakdown energy minus the rupture energy is extremely small.
Not necessarily, because it will depend the amount of slip that you will accumulate. So close to the tip, it is small, but then you can still keep accumulating breakdown energy, and particularly if you kick off a new weakening mechanism, as in the case here of thermal pressurization. So until here, the difference is quite small, but then you have this tail weakening mechanism that can bring significant differences. So it depends. Inside the plateau it is, but if there is another mechanism that kicks in, you can have a significant difference.
Thank you. Excellent.
Yeah, pleasure.
Very stimulating. Yeah.
Yeah, it really depends on when it stops slipping, right, Fabian?
Yeah, exactly. Yeah.
Yeah. So I'm going to stop the recording now and invite people